There are ponds in Southeast Asia that can produce more protein than cattle farms. No soil, no fields, no animals, just still water turning green. Most people think of it as pond scum. Some species double in mass in less than 48 hours. It contains complete protein, the same essential amino acids found in eggs. By land use alone, it can outperform meat, milk, and soy. For centuries, people harvested it as food. Today, almost nobody does. Not because it failed. It never fit the way modern food systems were built. This is the story of duckweed, the forgotten water crop that outperforms animal protein, and why it quietly disappeared. For most of human history, nourishment did not only come from tilled fields and grazing pastures. It came from living water. Ponds, canals, and wetlands were not empty spaces between farms. They were food environments. In regions across Asia and Africa, communities understood something industrial agriculture would later forget. The surface of still water was not a barrier. It was a garden. Where slow rivers pooled and monsoon rains collected, protein floated freely. No plows, no tractors, no slaughterhouses. The nutrients came directly from the water itself, absorbed by plants so small they could barely be seen. These systems required no irrigation because they were the water. They demanded no fertilizer because decaying matter fed the growth naturally. Villages that lived beside ponds thought of them as pantries. But modern agriculture drew a sharp line between land and water. Food came from soil. Protein came from animals. Anything growing on a pond was called a weed. That redrawing of boundaries erased entire food systems, and with them, the crops that made them possible. In the wetlands of Thailand, Laos, Vietnam, and Myanmar, a plant smaller than a grain of rice once blanketed entire ponds in sheets of green. The local people called it kai nam, water eggs. They harvested it by hand, scooping it from the surface with woven baskets. They stirred it into omelets, folded it into curries, dropped it into soups. It required no cultivation in the modern sense. You did not plant it. You simply let it grow. And it grew relentlessly. Under warm sun and nutrient-rich water, it doubled its mass every 2 to 3 days. In some species, under ideal conditions, that doubling happened in less than 48 hours. A single pond could be harvested multiple times per week without depleting the supply. Duckweed is classified in the Lemnaceae family, the smallest flowering plants on Earth. Some species measured barely 1 millimeter across. No roots, no stems. Just tiny green fronds floating on still water, multiplying faster than any other flowering plant ever recorded. For generations, this was not a novelty. It was nutrition. Only later did anyone ask what it was actually made of. For centuries, duckweed was food for the poor, peasant nutrition, pond scum. Then scientists began measuring what it actually contained. The results defied expectations. Protein content ranged from 20 to 45% of dry weight, depending on the species and growing conditions. That placed it higher than soybeans, higher than lentils, higher than most grains. But the composition mattered even more than the quantity. Duckweed contained all 9 essential amino acids, the building blocks the human body cannot produce on its own. The same complete protein profile found in eggs. Researchers compared its amino acid ratios to World Health Organization reference standards for human nutrition. Duckweed met or exceeded nearly every threshold. It was not an incomplete plant protein requiring careful combination with other foods. It was nutritionally whole. Laboratory analysis revealed something else extraordinary. Certain species contained vitamin B12, a nutrient almost exclusively found in animal products. A plant growing on pond water could provide what meat, milk, and eggs provided. The science was undeniable, but science alone could not undo what industry had decided. The biology of duckweed explains everything. Most plants invest enormous energy into structural tissue, stems to hold leaves upright, roots to anchor in soil, bark to resist weather. Duckweed abandoned all of it. Floating on water, it needs no support structure. Surrounded by dissolved nutrients, it needs no root system to search for minerals. Nearly every cell is metabolically active, dedicated to growth and reproduction rather than architecture. This efficiency translates directly into protein. While terrestrial crops convert sunlight into cellulose and lignin, duckweed converts sunlight into amino acids. It absorbs nitrogen directly from water and incorporates it into protein at extraordinary speed. The growth rate is unmatched in the plant kingdom. Under optimal conditions, certain species double their biomass in 16 to 24 hours. The fastest recorded doubling time for any flowering plant is 21 hours, achieved by Wolffia microscopica. No field crop comes close. This is not gradual accumulation over a growing season. This is exponential multiplication, week after week, limited only by the edges of the pond. Cut it today, and tomorrow the surface is green again. When researchers translated biology into agricultural output, the numbers were staggering. Duckweed can yield up to 30 metric tons of dry biomass per hectare per year. Soybeans, under ideal conditions, produce 2.5 to 3 tons. That is a 10-fold difference in raw output. But protein yield tells the real story. Duckweed produces approximately 2,000 kilograms of protein per hectare annually. Soybeans produce roughly 300 kilograms. Corn produces around 180 kilograms. Per unit of land, duckweed generates 6 to 10 times more protein than the most efficient field crops grown for animal feed. And it does this without soil, without tractors, without the fossil fuels required to plant, fertilize, and harvest terrestrial crops. Compare it directly to animal agriculture. Beef requires approximately 20,000 liters of water per kilogram of protein. Duckweed requires a fraction of that. A dairy cow converts feed into milk protein at roughly 25% efficiency. Duckweed converts sunlight and water into protein directly, skipping the animal entirely. The math pointed to one conclusion: for pure protein production, nothing on land could compete with what grew on water. Which makes one question unavoidable: why did this not become the foundation of modern protein? The 20th century transformed how protein reached human mouths. Refrigeration made it possible to store meat for weeks instead of hours. Railroads and trucks moved animal products across continents. Centralized processing plants replaced local butchers. Protein became a commodity that could be manufactured, packaged, branded, and shipped. This system demanded certain characteristics from its raw materials: durability, uniformity, shelf stability, crops that could sit in silos for months, meat that could travel frozen across oceans, feed that could be measured, standardized, and priced by the ton. Industrial livestock operations emerged to meet the new demand: cattle feedlots, poultry factories, hog confinement facilities. Each required vast quantities of feed grain, primarily corn and soybeans. Grown on mechanized farms designed for maximum output per labor hour. The entire system was built on a single premise: protein required land, fields to grow feed, pastures to raise animals, processing facilities to convert flesh into food. Water-based systems had no place in this architecture. They could not be mechanized in the same way. They existed outside the logic of industrial scale. As centralized protein production expanded, older food systems disappeared. In Southeast Asia, traditional pond harvesting declined as processed foods arrived in village markets. The knowledge of daily water harvesting faded within a single generation. Grandmothers who once gathered kai nam every morning watched their grandchildren eat imported protein instead. The replacement system operated on fundamentally different principles. Rather than harvesting protein directly from water, it grew protein on land, fed it to animals, then harvested the animals. Each step introduced inefficiency. It takes approximately 6 kilograms of plant protein to produce 1 kilogram of beef protein. The conversion ratio for pork is roughly 4 to 1. For poultry, closer to 2 to 1. Even the most efficient animal agriculture loses most of the protein it starts with. The system that replaced duckweed was not more productive. It was more compatible with trucks and freezers and supermarket shelves. It fit the infrastructure that industrial economies had built. But fitness for infrastructure is not the same as fitness for feeding people. The old systems disappeared not because they failed, but because they succeeded in ways the new economy could not measure. Duckweed possesses one trait that made it incompatible with modern food distribution. It is almost entirely water. Fresh duckweed contains roughly 95% moisture. Harvest it from a pond in the morning, and by afternoon, it has already begun to wilt. By the next day, without refrigeration, it spoils. This perishability posed an insurmountable problem for supply chains built around warehouses and long-haul transport. You cannot store duckweed in a silo. You cannot freeze it like meat without destroying its texture. You cannot ship it across continents without the specialized infrastructure that did not exist. The appearance created additional barriers. To consumers unfamiliar with water vegetables, duckweed looked like algae, like pond scum. Marketing it required overcoming instinctive disgust responses shaped by decades of separation between food and natural water. Processing presented its own challenges. Drying preserved the protein but demanded energy. Extracting protein created powders that lost the whole food context. Every adaptation required capital and market education that no company was willing to provide for an unfamiliar crop. The plant was not deficient. The system was incompatible. Global protein demand is projected to double by 2050. The land required to meet that demand through conventional agriculture does not exist. Water scarcity threatens irrigated farming across every continent. Climate change destabilizes the predictable growing seasons that industrial crops require. Against this backdrop, researchers have returned to duckweed with new urgency. Universities in the United States, Israel, and across Europe now operate controlled cultivation systems studying its potential for human food, animal feed, and closed-loop waste treatment. The numbers that once seemed interesting now appear essential. Protein yield per hectare can dwarf soybeans. Growth rates are measured in hours rather than months. Duckweed can thrive on water too polluted for other uses, simultaneously cleaning the water while producing nutrition. Companies have begun commercializing duckweed protein under names designed to overcome the stigma. Water lentils, mankai, ruby protein. Products are appearing in smoothies, protein powders, and plant-based egg replacements. The same crop that grandmothers harvested from village ponds is now grown in sterile vertical farms. The plant did not change. The world finally caught up to what it always offered. The story of duckweed is not about agricultural failure. It is about categorical error. We measured it against crops designed for soil when it was designed for water. We judged it by storage life when it was meant for daily harvest. We asked it to fit supply chains built for dead protein when it offered living nutrition that renewed itself without replanting. Duckweed was never a field crop. It was a living protein system, an ecological technology perfected over millions of years. It converted sunlight and water directly into complete human nutrition without the losses inherent in animal agriculture. It disappeared because food became an industry rather than an ecology, because we valued what could be stored over what could sustain. Because profit demanded control, and abundance growing freely on water could not be controlled. But the ponds never emptied. The fronds never stopped dividing. In Thailand, grandmothers still remember the taste of Kai Nam. The most efficient protein source on Earth was never lost. It was only waiting for the world to remember that food does not require fields. Sometimes it only requires still water.